welcome to today's tutorial on detect anomalies in machinery using an LSTM autoencoder in MATLAB. Myself, Shanti, I work as a senior online course developer at MathWorks, makers of MATLAB and Simulink. In this session today, we'll begin by defining the engineering problem. Next, we'll explore a solution to this engineering problem, walking through the key steps and considerations. After that, I'll guide you through getting started with MATLAB Online to ensure that you have the tools you need to follow along. After that, I'll guide you through getting started with MATLAB Online, and we'll move on to the hands-on activity where we will detect anomalies in machinery using an LSTM encoder, autoencoder in MATLAB. We'll end the tutorial by summarizing the key takeaways and a Q&A session at the end. I would like to emphasize that today's tutorial focuses mainly on MATLAB, how to develop an anomaly detector using an LSTM autoencoder without going too deep into theoretical concepts. So talking about the engineering problem we have today for the session, it's about how to detect anomalies in machinery. So modern industry relies continuously monitoring of machinery to ensure that there is reliability and to prevent costly failures. So vibration analysis is a key technique for assessing machine length. The problem statement we have today is to develop an unsupervised anomaly detector for industrial machinery vibration data. And the requirement is the detector must identify abnormal operations, meaning the potential faults in machines, using only normal data for training the detector. But developing such a detector with these requirements comes with several challenges. First, it's about imbalanced data. So most of the data we collect reflects machines operating under normal healthy conditions. Faults or failures data are very rare, which means that the data is highly imbalanced. The second challenge in designing such a detector is about having unlabeled anomalies. So even when anomalies occur or any fault occur, they are often not labeled in the data. So this lack of labeled examples makes supervised learning approaches impractical and forces us to rely on unsupervised technique. The next challenge is having complex time series signals. So mostly the vibration signals which we get from these machines are not only high in dimensions, but they also have complex temporal dependencies. This means the data points are not independent of each other. Patterns and anomalies can unfold over time, making it challenging to detect faults. So the main question or the central question is, how can we address these challenges and build an effective anomaly detector? So solution to this engineering problem is to use an LSTM autoencoder for anomaly detection. But the question is, why LSTM autoencoders? It's because autoencoder is a neural network that learns to compress and then reconstruct input data, effectively capturing the underlying normal patterns within it. And by combining autoencoders with LSTM or long short-term memory networks, we have an advantage that a model is LSTM model is specifically designed for sequential data, allowing us to capture any temporal dependencies which is happening in these time series data, such as our vibration signals from machines. So we achieve this with a series of steps which we will implement in MATLAB today. As a first step, we'll begin by loading a dataset that contains some statistical features extracted from the vibration signal. So in today's session, the process of feature extraction is not covered. But if you're interested in learning more about how these features are derived, you can always refer to the documentation pages, which I have linked in the additional resources section of today's session resources. After importing the feature table, next is we split the data into separate training and testing datasets. This is to make sure that to avoid any data leakage between training and testing. We then format the data as required by the LSTM autoencoder to ensure it is structured as sequences suitable for temporal modeling. And in the step 4, we define an LSTM autoencoder with specific parameters and specification of the model. And then once the model architecture is defined, we then move to training the model. So in this stage, we train the model to reconstruct the standard or normal patterns in the data, learning what healthy machine behavior looks like. So this is what the model will be trained on. And finally, we use this trained model to detect abnormal machine states in unseen data, which is our test data. So this way, we will flag potential anomalies that could indicate faults or that need for maintenance. So as a first step of finding the solution, we will get started with MATLAB Online. We will see how we can access MATLAB Online for this NPTEL course, Neural Networks for Signal Processing. And all the registered learners to this NPTEL course have access to MATLAB Online and these set of products. So we'll see how we can access MATLAB Online provided for this course. For that, we can go to the NPTEL course page for this particular course, Neural Networks for Signal Processing. And locate the MATLAB section on the left side in the course outline section. And on clicking on the MATLAB option, two options you will get, MATLAB Access and MATLAB Training. Click on MATLAB Access, which will give you set of instructions how to access MATLAB Online for this course. So as a first step on accessing MATLAB Online is to have a MathWorks account. So if you don't have an account, you can create an account using the link provided in step 1. And if you already have the account and you can directly go to step 2 and click on Access MATLAB for your NPTEL course. Once you click in there, you will be redirected to a page where you can access MATLAB Online for this NPTEL course. Click on Access MATLAB Online, which will take you to the MATLAB Online window. The URL to confirm, you can check the URL matlab.mathworks.com. Now open MATLAB Online. So this is a work script which we will be using today for the session. We'll wait for the live script to load fully. So I have the live script here. So the problem is to detect anomalies in machineries using an LSTM autoencoder. let's adjust the editor window so that we have enough space to work on the hands-on activity. So to reiterate, the problem statement for today is to detect anomalies using LSTM autoencoder. So as the first step, we will import the pre-extracted feature data. As I mentioned, the features are already extracted. You can refer to the additional resources link where I have provided how you can extract features from the raw signal data. Let's load the vibration feature data set with the .mat file provided. We'll use the load function, vibration feature.mat, and let's display the loaded feature to understand more about the feature table. Let's run this section. So here we have a feature table which has 17642 rows. That means that many signal samples we have. And we have 13 columns, indicating the first column is the label column and the rest 12 columns indicates different features that is extracted from the vibration signal. So the original data set which we have is three-axis vibration measurement signal. That means we had three channels, channel 1, channel 2, and channel 3. And through the techniques of feature extraction, we have extracted some statistical features from these three channels separately. And by applying some feature selection algorithm, we have identified 12 main features that will be give more information about the vibration data set we have. So likewise, we have a feature table created here. Now let's count the number of unique label category values in the data set. We will use a function called count labels. Count labels of features. Let's run this again. So here we have two categories. One category is labeled as before and the other one is labeled as after. This means before maintenance and after maintenance. So before maintenance, it will be more on normal plus anomalies or normal signals plus faulty signals. And after maintenance, it is expected that it will be on more on the normal vibration signal. So the label distribution shows that 35% of the samples were recorded before maintenance and 65% after maintenance. So this indicates the data set is skewed towards the after maintenance, which is the normal condition, which is typically in the real world example. We will have scenarios where we have more data sets on the after maintenance part. Now, as a next step, we will be dividing our data set into separate training data set and testing data set. For that, the proportion can be it can be either 80-20, 80% of the data set can be for training data set, 20 can be for testing, or it can be 90 and 10%. So for today's example, I am splitting the feature data into 90% of the data as training data and 10% as testing data. So we will use split labels function for splitting a data set. And we will save our index for after splitting in a variable IDX. So split labels of the first input will be our features, and the second input will be the percentage of splitting. Here I have taken 90% as training data, and I have also given a property called randomized. So that means it will be a random splitting. Let's run this section. So here, as the result, we got a cell array which has two rows. The first row is the training data, and the second index is for testing data. Now, with this index value, let's create the training and testing data sets. So let's save the training data set as ftrain equals features, the index value IDX. Since it's a cell array, we will use curly bracket for accessing the first row, and a colon operator which indicates we are extracting all the columns. So this will give you the training features in the variable ftrain. And likewise, we can save the testing features as well. So this will be f features of IDX, so second row, and all columns. Let's run this section as well. So here we get a table for ftrain, which has training features and training data set, and then ftest, which has which can be used for evaluating the model performance after training. Now, after splitting the data into training and testing, the next step is to format our data set in a way which is compatible for the model we are selecting. So here we are selecting the LSTM autoencoders. So LSTM network process sequential data where each input is a sequence or time series. And LSTM encoders in MATLAB expect their input as a cell array. And each cell will contain a matrix that represent a single sequence or sample. And each cell will have the matrix form, which has features of those signals, and features can be arranged either in rows or columns as per our requirement. So for this data formatting, we will define a function to convert our feature table. Right now we have our feature in the format of a table. So in order to make it compatible with the LSTM autoencoder, the model which we will be training or will be using for detecting anomalies, we need to format our data. So here we will be defining a function to convert our feature table into a cell array format where each cell contains the features of one sample. So let's write a function here. So since this is a processing for a cell array in cell array data type, either we can use a for loop or while loop, or we can directly use a function called self_fun. So the self_fun, what it does is it whatever function we are defining inside the self_fun will be applicable to the entire elements in the cell array. So we can achieve our task in a single line of code. So here what we have done is we are removing the categorical column. That means the label column from our feature table, because we are focusing more on the unsupervised way of modeling, right? So we are first removing the categorical column. So that's why if let's say the input is saved in a variable called in, we will select all the rows, which is indicated by the colon operator here, and the column we will select from the second column, because the first column, if you remember, in the feature table is the labels column, right? So we will select all the rows and the columns starting from the second index till the end. So first we are removing the categorical column, and then we are converting that matrix to a cell array, and the cell array will have a size which is equivalent to whatever size we have as our input, and then we are applying a transpose operation to make it compatible with the LSTM autoencoder. Let's run this function and create and define this function to convert a table to a cell array. Let's also analyze what happens if we apply this this function which we defined to our data set. Let's try it on our training data set. So now we are applying this function to our training data set. Let's run this function again. So as expected or as we wanted, the ftrain, if you remember, it was previously in a table format, right? It had a size 15878 cross 13 table. So now, after applying this function, it is being converted to cell array with the same size. So no information is being lost here after this conversion. But now the data type is a cell array, and each cell is having 12 cross 1 matrix. So that means each cell indicates the features which we extracted for each signal. So now our data preprocessing and data transformation part is completed. Now we'll move on to the section where we have to define the model architecture and train the LSTM autoencoder. So before going to the task where we have to define the autoencoder, let's see how do actually autoencoders work. What is an autoencoder? So an autoencoder consists of two parts, encoder and decoder. So during training, when we train an autoencoder, the encoder part, the first part, learns a set of features called latent representation from the input data. And these latent representation or these features are being used by the next stage of the autoencoder, which is a decoder. And with using these features, they reconstruct the decoder, reconstruct the original data and give it as an output. So autoencoders basically output a reconstruction of the input data we give. So this is how autoencoder works. And after this training happens, like after the decoder gives the output, it means that the training is completed now. So after training, the autoencoder now can predict input which it has not seen before, like our test data. So in case of predictive maintenance application, an autoencoder can be trained with the normal operating data, with the normal or healthy data, a healthy signal data, and it will give the corresponding reconstructed output. And that is how the autoencoder is being trained in the predictive maintenance application. And now the trained autoencoder is then tested on a new incoming data. Now what happens is, if an abnormal operating data is given as an input, it will do the same process. The encoder will learn features and the decoder will reconstruct it and will give the output signal. Now it will compare the output signal to the input data, and it will calculate a reconstruction loss factor. And if there is a large variation from the autoencoder's output, this indicates an abnormal operation, which means this requires some investigation or a fault is been detected in the input signal. So this is how an autoencoder works in the case of a predictive maintenance application. Now we'll see with our data set, our vibration data set, how we can train this autoencoder and use it for detecting the anomalies. For that, first let's set up the or we'll define the model architecture. So for that, we will be using an object function, deep signal anomaly detector object. So we will call the LSTM autoencoder as a variable called detector. And here what we have done is we have used an object function, deep signal anomaly detector. And the first input indicates that each signal to the detector has only one channel, which is a requirement for an LSTM autoencoder. And the next input is what type of autoencoder we are using. We are using here LSTM autoencoder. And the next parameter or specification for this LSTM autoencoder. As I mentioned, autoencoder has two parts. First is encoder part and the second is decoder part. The encoder, both of these parts will have hidden units. So the third input is we are defining the hidden units for encoder. So here we have defined two encoder layers with one with 16 hidden units and the other one with 32 hidden units. And the next one is decoder hidden units. We have defined it as 16. And we have specified the window length property as full signal. This indicates that the detector which we are defining, it treats each input signal as a single segment. This is a requirement for an autoencoder, LSTM autoencoder. And the thresholding method for setting the threshold to detect the anomalies is set to mean. There are different ways of setting the threshold, mean, median, and likewise. We have chosen here mean. And then the threshold parameter is set to 0.8. So this is how we define a model architecture. Let's run this function. Let's run this section and see the result. So if you analyze the result, I have the deep signal anomaly detector LSTM object with these many properties. And if you see the first property, which is trained, it is set to 0. That means the detector is not still trained now. We have just defined the anomaly detector LSTM autoencoder. And that also mentions the other model information which we have set. Now let's go to the next step of model training. So in the model training part, first we need to specify the training options. So what does model training means? Training means your model is, we are teaching it to recognize standard patterns in your data. So in anomaly detection with LSTM autoencoders, you train the model only on normal data, such as the vibration signals recorded after maintenance, because this is a real world scenario, because we won't have the faulty data set with us. We will generally have the normal data set. So the LSTM autoencoders, we will be training the model only with the normal data, which here in our case is recorded after maintenance. So as the first step of model training, let's specify the training options. So for setting the training options, we have a function called training options, and we can set any number of training options as per our requirement. So here I have set the training options as mini batch size is set to 500 and max epochs is set to 140. There are other training options as well. It's provided in the additional resources if you want to know more about the training options. I'll be sharing the complete script, the solution script at the end of the session. Let's run this section. So we have set the training options. And these are the different training options we have. For now, we have chosen mini batch size and max epochs. All others has been set to default value. Now we'll move to the training part where we train the detector. So for training the detector, as I mentioned, we will be training the model only on the normal data, such as the vibration signals recorded after maintenance. So for that, from the main F-train dataset, we will be selecting a subset, which is called train after, where we will select those signals which is recorded after maintenance. So from ftrain dot label, which is labeled as after, that means after maintenance. This train after dataset will be used for training our detector. Let's run this section. So we got a subset of our main training dataset, ftrain, as train after. So here we have only those signals which is labeled as after. Now for training the detector, which we already defined, and we have stored our LSTM autoencoder into a variable detector. For training this, we will be using a function called train detector. So this is the line where we train the detector using our filtered training data. But since this training, the model will take some time due to time constraint for today. What I have done is I have already trained the detector, and I have saved the detector, train detector, in a .mat file. So for today's session, we can just uncomment this line of code and see what is the trained detector looks like. So when you practice later, you can uncomment line number 47, which actually trains the detector using our specified training options. So let's run this section. This will give you the training options or training progress plot. We'll wait for the training plot to appear. Okay, so the train detector is being loaded. So if you see the output here, the detector object. So earlier, if you remember, is trained was set to 0. So now, after training, is trained is set to 1. That means the training of the detector function is completed. So after training, your LSTM autoencoder learns a compressed representation of normal vibration signals. Now, if you give a test data, it can reconstruct the test data set and detect the anomalies. So let's move to the next section of how, and we will see how our model detects anomalies with the test data. You can try out these examples later after the session. I'll be sharing the resources in the chat. Now, in the next step on anomaly detection on test data. So for testing the R detector, we will be using a function called detect. So this detect function will give an output, a logical array, which will be a combination of zeros and ones, and which indicates true for faulty signals. Now, in this section, let's count the anomalies in the testing data collected before the scheduled maintenance, and we'll count the number of anomalies as a percentage of number of signals. So for that, let's filter out the test data for entries labeled before. So we will write the code for filtering out the entries which has before label and save it as test before. Now, using the detect function, we will detect the events where to indicate which are detected as faulty data and which is detected as normal data. So we are using the detect function. The first input for the detect function is our detector, which is our trained detector now. And the second input is our filter test data, which is test before. And we have applied the data formatting using the function we defined earlier. And now we'll convert this detected events from cell array to matrix, so that we can count the percentage of detected events with respect to the total number of entries. Now, to check how many detected events are there in percentage, we will use n before, which is sum of a before, which is our detected events, to the total number of entries. Let's run this section and analyze the results. So if you see the results here, so this is the cell array, which as expected, which is the output from detect function. It's a logical array, which has zeros and ones, where one indicates this is a faulty signal and zero indicates this is a normal signal. And if you see the end percentage of the detected events, the model detected anomalies as 97.9% before maintenance. This is expected, right? Before maintenance, we expect a high percentage showing that the autoencoder is highly sensitive to deviations from the normal behavior. So because before maintenance, we expected there will be a lot of faulty data. So most pre-maintenance signals differ significantly from the healthy patterns the model learned. So we can say that our result from the model is a strong ability to identify abnormal conditions that may require maintenance interventions. Now, again, to validate if the model is working correctly or detecting correctly after maintenance, let's run the same set of code to a different set of test data, which is labeled as after. So here what we have done, we have in the next section, we have filtered the test data for the after conditions, and using the same detect function, we are detecting those events and then calculating the percentage of detections. Let's run this section as well. So here, now we got the results as after maintenance, a percentage is 6.3%. So the model detected an anomalies 6.3% of the signals collected after maintenance. So this is expected again, this low percentage showing that the autoencoder recognizes most post maintenance signals as normal. So we can finally infer that the results we got from our model, LSTM autoencoder, is very useful for predictive maintenance applications. Now, we can also visualize normal and anomalous signals to understand how the model interprets each signal. So we were telling autoencoders has two parts, the encoder part and decoder part, and it calculates a reconstruction signal and a reconstruction loss. And by the reconstruction loss, it actually detects the anomalies in the new signal. So now let's visualize to understand a bit more about normal and abnormal signal and the reconstruction loss. So for plotting these anomalies, we have a function called plot anomalies, which takes three inputs: our detector, and then the test data or whatever data we want to plot, and the plot reconstruction uh, property. So now let's randomly select a normal signal and an abnormal signal from the pre-maintenance test data set and plot these signals and its reconstruction signal using the plot anomalies function. So for that, first we need to detect anomalies using the detector and input data. So we will use the same detect function. So detect function also gives a second output, which has the reconstruction loss for each input signal. Now let's find out the indices of these non-anomalous plot. We already have the index saved in a before variable. So let's find out a non-anomalous data point, which is basically our normal signal. And let's randomly select one index from this data point. And we will use the plot anomalies function to plot the original signal and the reconstructed signal. So as I mentioned, plot anomalies is a function, and the input is, first one is the train detector, and the second input is a formatted data set, test before data set with a specified index, randomly selected index, and plot reconstruction is set to true because we need a reconstructed signal plot as well. Let's run this section and visualize the result. So here we have the visualization, which shows the normal signal and the reconstructed signal. So blue indicates the normal signal and the yellow indicates the reconstructed signal. So if you see, it is almost overlapping, which indicates there is no anomalies in the reconstructed signal, and the reconstruction loss here will be very low. Now we will visualize a signal from a category of anomalous category. So like the same set of code, we are selecting a random index from the anomalous data set and then using plot anomaly section to visualize the reconstructed signal and the anomalous signal. Let's run this section and see the result. So if you see the results, the raw signal is plotted, and the anomalies is indicated as red, and the reconstruction signal is indicated as yellow. And here you can see visible uh, difference between the reconstructed and anomalous signal, and the reconstruction loss is also more as compared to the normal signal. So no anomalies detected visualization. The reconstruction loss was in 0.7, which is very low. And in the anomalous signal, the loss function is higher, which indicates a faulty signal. So this is how an LSTM autoencoder is being used for detecting anomalies. So I have here added some additional resources as well. I'm sharing the solution script in the chat. You can download it, and I'm also uploading the trained detector mat file and the dataset which we use today. You can refer to the chat. And you can download this mat file, solution file, and you can practice later. I have a question here. Can we get these scripts in the NPTEL course? So I'll check if I can post it in the discussion forum, or else you can download the solution script and the dataset from the chat here in today's session. So hence we come to the end of today's session. So to conclude what we have done today, so in this example, we tackled a real world engineering problem of developing an unsupervised anomaly detector for industrial machinery vibration data. And the requirement was that the detector must identify abnormal operation using only normal data for training. So we used an LSTM autoencoder to solve this problem. And these are the key takeaways. We concluded that LSTM autoencoder effectively detects anomalies in industry machinery vibration data uh, with only using the normal training data, which is the post-maintenance data. And also we received a high accuracy, which shows good separation, achieved good strong separation between the pre-maintenance signals and post-maintenance signals with a high percentage, and successfully addresses all the challenges we were discussing in the beginning, which is imbalanced data sets and unlabeled anomalies and complex temporal dependencies. Yeah, I have shared the solution script in the chat, in the same session chat. You can refer to that. Please confirm if you are able to download the solution script and two .mat files. Please confirm in the chat if you can download the solution script and two .mat files. The two .mat files, one mat file is the dataset we use today, the feature table vibration feature .mat, and the other one is the train detector .mat. Thank you for joining. If you okay, not able to download the vibration, I can reshare the file once more in the chat. I have reshared the mat file. Please try once more. Okay, thank you. Thank you for joining. Um, Thank you all. You can refer to the additional resources links also provided in the solution live script for more information. Thank you. We can close.